Go!
Hello, everyone. Welcome to Practical GCP. In today's session, I would like to talk about a real-world use case to tackle a delta tracking problem using the BigQuery MERGE function. So in this session, I would like to cover a number of sections. So that includes what is DML MERGE, just a very quick introduction about it, and also to cover a real kind of delta tracking scenario as a kind of visual representation. You can see what it looks like and what kind of problem we try to tackle. One very important function in BigQuery to mention called JSON String. We'll talk about that. And then we'll run into a real example in action and how the delta tracking actually works with some example data from TFL cycle. And lastly, I would like to cover a few things about the information on the DML part of BigQuery. Okay, let's crack on. So first of all, the merge statement, in a nutshell, what it does is you have typically a target and a source. So these are basically two tables, right? You have the one that has the source, where the data is coming kind of from, and you have the target is where the data is going to. The merge is basically performing based on certain conditions, then you can perform certain actions. The direction of travel is always from the source to the target. Okay, you can read more about it on the documentation side, but the focus of this session will be more on the practical use case side of things. So now let's look at an example in this diagram. So this is I would say, a quite typical use case on a kind of data engineering problem where you have a source system that can be pretty much anything. It can be a database, has a table you're getting the data from. It could be an API. It could be any kind of things. So you typically get that data into your system. Then you have let's say you call that the current version of it, right? You have this external system you need to send the data to. So if you just use this current version to send your data to the external system, that can be quite complex in the sense that you typically can't do that in many scenarios because this current version can be very big, right? So you've got this external system that typically has issues handling large amounts of data. But the most important thing is it actually necessary to push that much data from this current version into the external system? Let's say if you have 1 million rows in here, are you just going to push all that 1 million rows into the external system? In the majority of the use cases, this is not only very costly, time consuming, and also just you basically waste a lot of resources in doing so. So this is where the BigQuery merge statement comes in. Typically what we do is you've got this current version, but you also have the snapshot. Now, this is your source and this is your target. We typically use the merge statement to perform a hash comparison based on the data you actually care about that is changed in this process. And then once you've done that, in the snapshot, you will know what is actually the difference in this particular case using a timestamp. And then you can push that into an external system. So as a result of that, you're only pushing a very small amount of data from the snapshots into the external system. So therefore, the cost is much, much lower, and the amount of time that you spend doing this on a daily basis is also probably in a lot of the use cases talking about seconds instead of hours if you can actually detect the delta. Okay, next, let's have a look at the JSON String function in BigQuery. This is something that is really important that we can use. I would say more for convenience in the sense that how to track the delta. So this is something you can use as a way to extract information from a BigQuery table column into a JSON format, such as this. The reason for using this, I'll actually give you a real example just in like a little bit in the next slide. So it's more straightforward on why we want to use this and why this is a very convenient way to use to be used in the process of computing the delta. Okay, so now I'm in the sandbox project with some example data where we can actually look at how to really kind of perform the delta tracking process. So I've got some example data already copied across from the BigQuery public data set. So these are the London TfL bike stations in this particular table. The table here, you have, in this case, an ID, which is the primary key of a station. We've got many other columns, so they're kind of irrelevant. It's not really important to understand exactly what they are to understand the use case here. The important thing is there are lots of different columns here, and they can change, right? The next day, if some of the information has been changed in any of these columns, you'd want to find out what they are. This one, obviously, you can see there's only 787 records. It's a very small table, but in many real-world scenarios, this can be very large, very significant. Let's say if you're dealing with customer information, you can be dealing with many other scenarios, which you could be talking about, tens or even hundreds of millions of records. Sometimes the systems like this, you may not be able to track the delta at the time the data comes in. So this is where this is important, that you can find out what has been changed and to then use the delta to push to external system rather than just pushing the entire thing. So let's have a look at the current version. So this is the same as if you remember in the diagram here, we have this current version table. So we'll jump into Snapshot in a bit. Let's focus on the current version first. In this current version, it's basically a dump of the whole 787 records from the cycle stations. And this is kind of mimicking. This is something I've done ahead of this session. It is mimicking a typically daily or hourly ingestion process that you get the whole thing here. You get the whole full table in, because there's no way in the upstream system, in this particular case, in the BigQuery public data to tell you what has been changed. They just give you a dump of the current version. So the first step is we get that current version back. But in this process, you probably notice there's one additional column called delta hash. So this is a computed hash of all of the relevant columns that we care about. So what that means is we don't really care too much about the ID column because that's the primary key and it would not change. If it changes, that's not the same station anymore. But for the rest of those columns, all the way from installed to removal date, these columns, any of these columns can change. And if they change, we need to know they have been changed. And then that is the delta we need to track. So I've prepared a query ahead of this session. So I can just show you how the toJSON string function we mentioned just a couple of minutes before can be used in here. When I run this in the cycle stations, I have included all of the columns I care about from installed into removal date. Because the toJSON string function can only be applied to one column. So what I've done here is I've converted the combination of all of these columns into a struct. And then that can be converted into a JSON representation and therefore converted at the end, converted to a SHA 256 bits hash. That's where this hash is coming from. So before we move on, I would just like to show you what the toJSON string gives us if we don't actually convert to a hash. This is quite interesting. As you can see, it gives you it converted all of these columns, because keep in mind, this is a struct. It converted all of these columns into one JSON line, right, with all of the key and values. This is very powerful. And at the end, you can see this column, the removal date is currently null. Imagine if you don't use toJSON String, you would use something like a concatenation. If you have a null column, the whole thing would become null, right? But if you use the toJSON String function, it will actually convert this into something that is always going to be a JSON representation of the whole thing, right? Regardless of if any column is null. But what we care about is if anything here in here has been changed, we want to know, right? Let's revert a little bit into the hash part. To convert this to a hash, the reason we convert this to a hash is so that we can store this in the version of the current version table, and also in the snapshots later on. So we can actually use the hash to compare things rather than recompute this every single time from the source data. We will compute it at the time of writing, and then when we need to do the delta comparison, we can compare. Not only this is more efficient, but at the same time, you can see if something goes wrong, right? You can actually see why they're different, right? Why the hash is different. Has it actually done the right thing? So you can see all of these details. That's why we store them here as well. So now we have the hash. The snapshot is currently empty, right? This doesn't have anything. It's just the same schema with the delta hash column as well. But as you can see, we also have a last updated column here. The reason we have this column is because so every time when something happens to this table, right? Because we're doing a merge here, we're sending data to this table, we might be updating data in this table. BigQuery has a feature called the partition table that you can use. You can partition the table, partition any tables in BigQuery for cost saving. You can put it this way. We'll talk about partition table in a separate section on some real use cases. But for now, you just have to know that if you partition a table in this particular case based on a timestamp column, when we're querying the data, we can actually save costs by only querying the data within certain date time blocks. So then we don't have to scan the entire table. So obviously in this use case, this table is quite small, but in reality, when you're using when you're tackling your use case, this could be a lot bigger. So this plays a really important role. And that's why this is a partition table. Right, so now we know the structure of the current version, and we know the snapshot, which has this additional column. Everything else is the same, right? Okay, now is the time to come to the merge. I have prepared another query here. That is the merge query. Don't worry, it looks quite complex. We'll run through this section by section. In this particular case, we've talked about this is coming from the source, which is S in this particular case, into the target. So just to repeat that, the syntax here we can see is coming to the data, the comparison is between the source, which is S, and the target, which is T. It's a typical recommended practice to actually label them with S and T. So you know when you're actually writing your queries, you know which direction, like which part is actually using that comes from S, and which part is coming from T. But the source is the current version, and we want the merge in go into the snapshot, right? This next line, the on statement, is the condition of the join. So it still performs a join between the source and the target. So when you compare the two, you typically want to compare based on that something that is linked together. So in this case, we're using the primary key. So both tables have an ID column, right? And that is unique. When we check the ID column in this case, this is the basis of the comparison between the two. So that you use this to link the two together. So once you link the two tables together, that's when you set the different conditions. So in this first condition, this block here, it says when matched and the delta hash comparison, then do an update. What this means is if matched, it means if the source and target ID has a match, you can see this as like an inner join. So it's joining the two tables together using the primary key, right? That's the match. So this condition is passed. Then if the delta hash is different between the source and the target, so this is really important. If you have a matching record, let's say the ID is 200, right? You have a source and a target. Now you're comparing the hash. If it's the same record on ID 200, now you want to compare if the hash is the same or not. So this is where you compute the delta. If they are not the same, right? If they're not the same, it will get into this section. And what it does is to say, okay, now you have a matching record on ID 200, but they have a different hash. What I want to do in this case is to do an update in the target, right? These are just all of the columns you care about, you wanted to update to make sure they are updated correctly in the target. There's one thing to pay attention to is this. So there is a last updated column that you need to update to. When you update that, you would always want to use the current timestamp. Why is that? Because it's the partition date. So this record, once it's updated, let's say ID 200, it will have a last updated timestamp of right now. That is particularly useful because you know after this query runs, once you track the date delta, you know the exact timestamp of when this primary key row 200, ID 200 has been changed. And also, of course, you want to update the hash at the same time. So you know the hash is now the same between the source and the target. There's another condition we have in here. This is useful because let's say in the case, well, okay, right now our target table is actually empty. When it's empty, you would not have a match, right? Because the ID from the source and target, in the source, you would have 700 odd records. In the target, you have an empty table. When you're doing the comparison, the first condition would not be matched, not even on the first part because they don't match. When you get to the second part, because there is no match, right? There's all the IDs in the source, they don't have a match in the target. Then what it will do instead is to perform an insertion. This will basically insert all of the records from the, in this particular case, that don't have a match from the current version into the snapshot. So in this case, you can see this block is just the insert statement. There is another syntax you might find out. You can just do a shortcut of insert something without specifying all of the columns. Do not do that, because if you do that, it will become a positional thing. And then if you swap around the columns names, things will go wrong. It is always useful and always critical to explicitly write down the insert all of the columns, right? In all of the columns you would like to insert in this insert, and all of the values you would like to insert. So these are the schemas in the target table, and these are the values you're getting from the source table. Again, pay attention to the last updated column. When we're doing an insertion, we also want to make sure this is referring to the current timestamp again, just like when you update it. When you insert it, you also want to know this has just happened, and then you get a current timestamp that's right now, and you have all of these records in the current table. Okay, let's run this. Now you can see there are 787 records has been updated in the snapshot. That's the merge operation has been performed. If I run, okay, let's have a look at the snapshot first. You go to the preview. In this case, you can see there are 787 records, and they're all being inserted. You have the delta hash, and you have the last updated timestamp, which is right now. This is really useful. Okay, now let's perform one more action before we move on to the last bit of how do we export this, the best practice we should follow to export this to the external system. So in the current version, now I'm going to make a change. I've prepared another query in here. This one, I've basically put a random string in the column that has oops, apologies. So basically, between longitude and we've got another. This, I believe this is the name of the bike, but the station. So I've replaced it with a random string. So this update statement, all it does is trying to update the delta hash and update the name of the station. It's just assimilating something has changed, right? It's like when you have a new ingestion coming in, let's say everything else has remained the same, but ID 200 has been changed. I run this one. It tells me one record has been modified in the current version. Okay. Now we perform the merge again. Remember, when we ran the merge the first time, we have 700 odd records in there. And now we run it again. We should only have one that going into the target because there's only one row has been changed. Let's run that. Cool. You can see now the snapshot has one row has been changed. Let's run this again to see what happens. 0 rows has been changed in the snapshot. So this is actually really good because as you can see now, it doesn't matter how many times you run this, it will not have a side effect because your target is already up to date with the source. Let's have a final look of the target table. You can see here, the target table, these are all of the, you can see these all have the same timestamp. The operation has happened in the previous one, in the previous run. And then the latest run, this is for ID 200. Let's find the ID 200 to see whether if that's different. So this is 162540, right? If we find out the ID equals to 200, and you can see it has a different timestamp. It's on the 28, and the hash and the rest of the data. And you can see the name column has been updated to random hash. So this is where we track the delta, right? So now, imagine now you need to send this data, the delta, into the external system. The first day, obviously, when you first run it, everything is changed, right? All of these records have the same timestamp, and they all have been changed. You push everything into the target system. It's just this is called a backfill. You always have to do that in the first run. When you run it the second time, you know what is the latest timestamp of your previous run, right? You can keep that state somewhere. It could be in another BigQuery table. It can be anywhere. Let's say you know now your latest timestamp where you have done the previous run is 1625, right? You have that timestamp. When you run this again, you can simply say anything that is greater than that timestamp. In this case, it will only pick up run record and it will send it to the external system. This is a really powerful thing because if you run your upstream systems ingestions, let's say every hour or every like 10, 20 minutes. If there is no change, you simply push nothing to the external system. If there are lots of changes, you push those lots of changes to the external system, but you never push millions or hundreds of millions of records into the external system and crash it. This is really important. So hopefully that's very clear. Okay, that's how the merge works. And this is the very practical use case that from my experience, many companies have used this to track their internal deltas and keep things up to date with external systems. And this is where you can scale, not only, so let's say you currently have something that runs daily because you're worried about the pushing too much things to the external systems. And now with this delta tracking mechanism in place, things can be so much cheaper compared to you just push the whole thing into that. Hopefully that makes sense. So finally, I would like to cover something to do with the DML features that BigQuery offers and the things you probably want to consider. And there's actually some of the good news in this area as well. So the DML section in this case is really important that you have a look at, well, this is not only just DML, it applies to pretty much all Google services, that you need to pay attention to the limitation or quotas section. So when you use it, there's typically only certain things you can do. There's like timeout, there are like how many concurrent, if you look at this, concurrent mutating DML statement per table. So these are the things you typically want to have a look at. So when you design your systems, you don't fall into some of the traps that actually doesn't work after you design this thing. So you must have a look at these quotas to see what it supports, what it doesn't support, and where are the things that you don't want to design towards to. But there are also some good news. This is an article Google published back in quite a while ago, March 2020, but I'm not sure if everyone's been tracking on the Google blogs on a daily basis. So if you've been using BigQuery for like a number of years, you probably in the past have been very careful in how many DML you run on a daily basis per table, or there's even a project DML limit. But this has been no longer the case since March the 3rd, 2020. All of the DML, all of the DML restrictions have been lifted. So you can typically run as many DMLs as you like. So this makes the merge. So in the past, when you have to consider this is the so many merges you can run, you only have this many capacities you can do in a day, but now that's not a thing anymore. So have a read about this. Have a read at this article that Google has written. It's very good, explaining what has been lifted and what you can actually focus on with the merge, with the DML and other DML functions. And this is a very powerful feature indeed. So that's the end of the session. And thank you very much. I will see you soon. Thank you.
Go out.